When the water level is 6 feet deep. And when they said water's going into this tank, right?
Mm-hmm.
How fast?
9 feet, feet per minute.
So if we want, maybe we'll just go like this. We'll put like here, 9 cubic feet per minute. Here comes the water. I'll draw an arrow. It's going in. So that means volume will increase, right? Sometimes they do the leaking faucet stuff or the leaking cone. So keep that in mind. How fast is the water level rising when the water level is, how deep?
10 feet.
At 6 feet, right?
Yeah.
So in that number 6, I don't plug that into the very, very end. Right? Seriously. Once I get it all set up, once I differentiate, and I got a little h in there, because h will be 6, right?
Mm-hmm.
Do you follow me? But at the very, 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 very end, maybe I won't even write it down now. I'll wait till the end. I'm just going to plug in 6 for h. Okay?
Why would you? Oh, because 6.
We wait till the end, don't we? Didn't we do that with this problem?
Yes.
The same, very similar. We start with the actual formula. When we get it all broken down and neat, then we start substituting numbers. True?
So then h would be 6.
So I'll let h equal 6 once I get the whole formula worked out.
Oh.
Cool? But we got to start with the formula. And on what is volume of a cone? 1/3 pi r squared h. We'll start there. Now, make a note about cone problems. Look how many variables there are on the right side of the equation.
3.
And just go to the right.
Two.
On the right side of the equal sign, everyone. There's an R and a what?
H.
H.
Product.
And he's like, you're hitting on it. You're like, we'd have to prodigal, but we're gonna do even better than that. Every time we do a cone problem, with related rates, everyone, we're gonna start the problem with one variable on the right side.
We're gonna
That variable's gonna be height. So we're always gonna start this problem before we even differentiate and get everything in terms of h.
Okay.
You go, why? Because geometrically, there's a nice little relationship going on between the h and the r, because if you've taken geometry before, there's something called similar right triangles. Have you ever heard of that? Triangles that are similar?
Uh-huh.
And so do you see like a triangle in here? Like this thing shrunk to here, and then it's at what, how high? Maybe 6. So you see that, I'm gonna draw 2 triangles here. This is just a geometry concept, but I wanna show you why we can eliminate r at the very beginning.
Okay.
There's a relationship, and there's similar triangles. 2 triangles are similar in all geometry, as long as you've got 2 angles congruent to 2 other angles. Well, do you see this triangle and this triangle?
Uh-huh.
Don't they both share that angle?
Yep.
And have you ever heard this phrase, alternate interior angles are congruent?
Uh-huh.
And then I'll put 3 here, these angles are equal. So what I'm saying is, every time you have this type of design, with the triangle, which is true with the cone, you have similar triangles. And that means, in this case, we could say like, let's say I'll put this triangle out now. Here's the big triangle, this is the what?
Small.
Small triangle. I can say like, this letter, I'll call it D1, I can call this D2. These sides, corresponding sides are in proportion. So if this was like, I'll call this L1, L2, but you know what we could say? D1 over D2 is proportional to
L1 over 8.
L1 over L2. You can do that, it's a rule of geometry, it's a theorem, deals with similar triangles. So I want to point out, you always have similar triangles in there. So to start out with, everyone, let's do this. First of all, I want to write this whole equation in terms of what?
H.
All right.
So that's 3v over pi r squared, right?
Oh, I love it. I love it, everyone. So I want to write this whole thing in terms of h. So I need a relationship between r and h. All right? So, how about I do this? Now when I'm gonna solve for R. Let's write this. R is to H. This must always be the proportion in this picture, but I need you to go into that image right there and tell me the radius and the height of the entire cone.
10 over 10.
What's that height right there, Amber? 10, so I'll put that here, and I need to look closely.
Oh, 5.
What is the radius of this
5.
cone? Radius is from the center out. Someone agree?
Uh-huh.
Yeah.
Good,
Did
Josephine.
you get the R over H?
I just wrote it as a proportion.
Why?
Because
Similar to-
of this, what I just explained for 2 minutes. With these two similar triangles, we're gonna be able to write this R in terms of H, because this proportion will always hold true. So what I want you to do, Josephine, is always write R over H with the cone problem. Cool. So now, what's his radius?
5.
What? So always do this with the cone, but what I need you to do now is solve for R. Can you do it? Oh, you might reduce this. What's 5 over 10?
Half.
R over H is that a half?
Mm-hmm.
Alan, can you isolate R?
Yep.
QR equals.
No,
Well,
no.
how would you get that H off that side?
Divide by 8. So
I've
basically,
got R over H equals a half. How can I get R by itself?
half of R.
I can multiply an H on both sides, right?
Yep.
What do you get?
So half of 8.
H over
Two.
2, is that what I got there?
Uh-huh.
So, I mean, what is the continual relationship? Always in this cone. Radius will always equal half the what? Height.
Height.
Throughout that whole thing as it fills up. And it's because it's similar triangles. So every time we do a cone problem, and I like your question, Josephine, you and I are gonna go off to the side, before we even differentiate, here's the formula, we're gonna say, well, what's R to H in this entire picture? So even if this was like 30 and this was like 28 or something, find the radius, find the height, set that ratio to this, and then solve for what letter? R. Because now, where can I substitute this? Where's this going? Right there. Before we start the problem, we can write everything in terms of one variable, H, every time with a cone, because of geometry. So you'd want to do that. And here's the other thing. Remember you said Bell-Rage product rule? Great, but see, we weren't given any radii distances, were we? They didn't tell us how fast the radius was changing. That's why we want to do this. The only thing they told us was how fast that water was coming. So, everyone, what do you get?
So 1/3
1/3 pi. Don't forget there's a squared there.
H over 2 square.
Right, H over 2. I think I'll put it in yellow just to emphasize it. Look at this, everyone. Boop. There's R. Well, what was right next to that, huh?
H.
Now, I encourage you, everyone, before we do differentiation, can we simplify all that junk?
Yep.
Make that look a little prettier, Amber. All this junk in here. What do we got? You got H squared, you got a 2 squared in the denominator, and you got an H over here.
So H cube over 4. 1/3
So you got a 1/3 pi
H cube over 4.
H squared over 4 times another H. And then Art just told me H squared times H is H what?
H cube.
Cubed. Everyone, what's a 4 times a 3 in the denominator?
12.
Pi over 12 H cubed. Oh, that's so pretty now. Oh, there we go. That's where we're starting. I haven't done any differentiation yet, right? But let me rewrite this whole thing. Here we go again. What's volume equal to? Pi over 12 times
H cube.
And the beauty of this, Josephine, we've got one variable. We're saying volume is in terms of one variable. It's not an R and H number. And you can do that every time with every cone. If the cone is tilted this way or if it's like this. Because one of the problems in the book, they got like sand, a pile going like this. It's building up. They're pouring sand. And it's like one of these conical piles that just keep building like this. You do the R over H. And then solve for R so you get it all in terms of A. And you go, Evan, why don't we do the opposite? Solve for H and then put it in terms of R? Because then when in real life, it's really difficult for something to go inside, like, let's say this is water, some kind of fluid that could harm me. It's tough to get in there and say, oh, how far is it from there to there? Where is, I'm on the outside of this thing, I don't know how far it is that way. This is easy to measure. It's easy to me, just get out a ladder and get up, this is the height. So he's talking height. All right, let's do it right now, everyone. Ready to differentiate? All right, D, what's that letter?
V over dt.
All right, that would be rate of change of volume with respect to time? True?
Yep.
You ready to do power rule with the chain rule? You know afterwards I'm gonna put a DH what?
dt.
DHCT, but help me do power rule. 3 in front.
So 3h squared.
Some might go, wait, do we need product rule? No, that's a constant. 3 times pi over 12. Decrease this by what? H squared. And then write?
dh dt.
DH dt. Implicit differentiation, chain rule. Hey, can we reduce 3 12ths?
Yep, 1/4.
So I'm gonna write it again, just because we're gonna reduce that 3 times. dv dt is pi h squared over 12 dh dt.
4.
Oh, thank you. Now, where do I put the 9? I think the units give it away. You know, there's two things. Is the 9 here? I'll be grading tests. People just throw down a 9 here, or they throw down a 9. Where's the 9?
dh dt.
DVDT.
And 6 goes.
How do you know what's DVDT is the 9?
It's feet cubed.
Feet cube per hole.
I love it. You're looking at, I'm going to use these tactics, these ideas. His suggestion is because it was feet cubed. Look, cubic feet. That's changing what?
Volume.
Volume. So if you're concerned like, well, I don't know which one to put, look at the units, it'll give it away, right? That's 9 cubic feet, that has to be that. If you're confused, like, I don't know which one it is.
But how do you know it goes down there?
You know it's here, Amber, because of this thing, right?
Cubic, yeah.
Cubic
Yeah,
feet,
velocity.
you're like, that's change in volume, DVDT. Now, before I screw up, help me out, is it positive 9 or negative 9? It depends. Is the water going in the cone or out of the cone?
And so it's
In the cone,
positive.
so it's positive, good. Good, volume's increasing, good. And finally, at the very end, everyone, I recall 5 minutes ago I said something about the last sentence said do this when the height of the cone was how high?
6.
6. When the level of the water was 6. So put a 6 in for H. And we can solve for DHDT. All right, 9 equals pi times 36 over 4.
Isn't it going to be 6 squared?
What's 36 over 4?
9.
So 9 equals 9 pi.
You can cancel 9 out.
Divide up 9 on both sides?
Mm-hmm.
Amber, okay? Yeah?
Yeah.
What, divide 9 both sides?
Yeah, divide 9.
Nice. Last step, divide the what?
By pi.
Just leave your answer like that. Just leave it like that, unless you want decimal. That's exact. Now, what's my units? I have to put units. I have to put units.
Feet per.
Feet, cubic feet.
Feet per minute.
Feet per minute.
Belrash, excellent. He goes feet per minute. That was change in height. That's the length, right?
Mm-hmm.
Before you think, wait, do I do cubic here? How fast was the height changing? When it was 6 feet high, the water level. DHDC, feet per, it was minute, right? Yep. 1 over pi, feet per minute. Yeah? So I love all your questions. Josephine, I loved yours. She's like, what are you doing with this R rate? We'll always do that when it's a what? Cone. It's not like there's a bunch of cones, but everyone, would you look at number, we won't do it now, but you might say, hey, can you do it tomorrow? Look on page, where is it? Top of page 249, what do you see? What image? See it?
Corner, okay, yep. Number 27.
But I'd like to do one more related rate. Let's find a good one, okay?
Or we do another one like that. It's not like that.
Oh, I think tomorrow, I bet you we'll do another cone problem. I'm telling you, the one that had it, there's a gravel pit. Number 27, see this?
What page?
You don't have to do it now, but you definitely
249.
try, if you want to try it tonight, Aaron, we can do it tomorrow. It's in the related rates, it's on page 249, do you see it? The top of page 249, can you see an image from here? They get this gravel and they're pouring it down, it's forming that cone. And before you even get the problem in, doing differentiation, you're gonna what? You're gonna average.
You have to do it for every compound.
That's right.
Average, okay.
Because they don't give you information on the radius and stuff. I guess you can H over R, but still just solve for the letter what, R? Cool. Alright. For, Amber, do you want to hear the first few words of number 23? Water is leaking out of an inverted conical tank. Alright. Hey, we already did 2 right triangles. I think we had enough of the right triangles for the day, true?
Mhm.
Do you agree? But let's definitely do another right triangle tomorrow. Because before you think, I've got right triangles down, sometimes the problems in the book, let me read it to you. Listen to this problem. Make me do this tomorrow. There you go. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour. Ship B is sailing north at 25 kilometers per hour. Then they go, how fast is this between the ships changing at 4 p.m.? We've done enough right triangles today, but let's do a problem like that tomorrow. Because, do you notice they said what's going on at 4 p.m.?
Uh-huh.
So we got to think about how big that triangle got after 4 hours, true? We got to make a really good picture. And it all depends where these ships were at the beginning. Cool? So we'll do 14 tomorrow, but I think